Hello and howdy Algebra 1 students. Welcome back to Topic 7. We're on Lesson 7.3. I really enjoy this lesson because it's really going to bring everything together that we've done all year long. It's also, of course, going to review what we've done in Lesson 7.1 and 7.2. So the title of our lesson is Solving Quadratics by Graphing. Our opener asks you to graph three different equations, and I'm going to give you some hints on each one of these as well. Our first equation should look very familiar. F of x equals 2x minus 4. Just a reminder for each of these, f of x, g of x, and h of x. If those f of x, g of x, or h of x notations scare you a bit, you can always change it to a y. And then, doesn't this look a lot like maybe mx plus b? And we should know that mx plus b makes a line from last semester. What kind of line? Well, it's going to make a diagonal line. Especially with a positive slope, it's going to look something like that. My hint for g of x is that this is an exponential function. So exponential functions are going to take the form of b to the x power. And there are two things that you need in order to graph this function. We don't have to be very accurate. We did this in topic 6, but we need to know two things. First, we need to realize that b is our growth or decay factor, right? We call it the common ratio. So you're going to decide, does that 2 make this exponential growth or decay? And then my other hint is you're going to really want to find that y-intercept. I think once you do those two things, decide if it's growth or decay and find the y-intercept, you can sketch a pretty decent graph. Last but not least, the most simple looking equation, but the one students tend to forget the most often, y equals negative 4. All right, well, what that tells us then is that there are a series of points on this graph. The equation does not have anything to do with the x. You can choose anything you'd like. But we do know that the y value has to be negative 4 every time. So take those hints to heart. Let's see what you can do with these three problems. And then once you're done, we'll come back together, see how you did, and introduce or reintroduce what we're trying to do for today. Okay, so hopefully each of these weren't too bad. I'm just going to quickly go through. Our b was negative 4. That's the y-intercept. It's the beginning. Our slopely right is up 2 over 1. And using that, we can create our marvelous linear function, linear graph, I guess. It is diagonal, and we're done. The second one, we need to realize that if you multiply a number by 2 over and over and over again, that's what the x power means, then that number gets larger. This is an exponential growth function. Where is the y-intercept? Well, for any function, to find a y-intercept, we replace the x with 0. We do need to remember that any number to the 0th power is always 1. So we input 0, got an output of 1. Now we have the y-intercept. We should also remember that an exponential growth function will sit right along the x-axis and pretty slowly grow until the y-intercept, and then grow very quickly after that. Now, again, these points are not super accurate. If you wanted to be more accurate, you could start substituting in other numbers for x, 1, 2, 2, 4, 3, 8, and it does get very, very steep. For today, though, for the exponentials, you don't need to be that accurate. And let's go ahead and look at the third. If you fill in a few x values, I'm just going to be boring and do 0, 1, and 2. This gives us the point 0, negative 4, 1, negative 4, and 2, negative 4. Hopefully by looking at that pattern, you can analyze and see a horizontal line is created by doing y equals negative 4. We have actually learned 4 types of graphs this year. The very first graph we learn are linear functions, whether diagonal, vertical, or horizontal. We see that on f of x and h of x. The second type is actually a variation on linear functions. It's linear absolute value. An absolute value makes that V-shaped graph. The third style of function were those exponential functions that we did in the middle. And the fourth type of function is what we just learned in 7.1.7.2. Those are quadratics, which make what shaped graph? A U-shaped graph that we call a parabola. Now remember, we try to understand all equations in at least 3 perspectives. Graphically, how to graph them, what do they look like graphically? We did that in 7172. Algebraically, can we isolate x? And in a written manner, if we have a type of word problem, real world problem, can we create an equation that works with that problem? Now, algebraically, we actually are going to struggle to solve a quadratic equation. But let's try one just for fun. Go ahead, please, and isolate x in this quadratic down below and write your answer on the right. I'd like to give you about a minute or so, and then I'll address some common misconceptions and successes that I see from students. Ready, set, go. All right, let's run through a couple common mistakes that I saw students make. And honestly, some of these mistakes I don't blame you for at all. They're a very logical step. Over the next few classes, though, we'll do our best to explain why they don't work. So the first option that I see, and I'm going to zoom in here, is I see students take the 2 that's out front and they try to distribute that 2 to the inside of the parentheses, because we've been so well trained that when you see parentheses, you distribute. Well, this is not an exception to the rule. This is really understanding that that rule isn't a very good one. In fact, the times you can distribute are pretty limited. You are only allowed to distribute, can only distribute, and I'm going to abbreviate that, when there is no exponent. Technically, that means that there's an exponent of 1, but we're just going to say no exponent. If there's an exponent there, it kind of acts as a blocker. We'll find a few ways to get around that, but for now, we don't know it. So then the second option that I see is directly taken from topic 6, what we just learned, and it's a great move. There's one thing you'll need to remember about it. The move that I see people make is they try to take this square and distribute it inside, because we did learn last unit you can distribute an exponent, but you can only distribute an exponent to multiplication or division, not subtraction or addition. But I just wanted to say that because there's subtraction in the problem. So unfortunately, we are not allowed to distribute the exponent either. Nah, bummer. Well, then we get to the last option I see from students, and it's a great option because it's actually the right option. And so I'm going to take a little bit more space here. Option 3 that I see is they take this 2 times x minus 3 squared equal to 2, and they go through and divide off the 2 because of the multiplication out front. And that's a great step. 2 divided by 2 is 1. We don't need to write that anymore. That leaves us with x minus 3 squared equals 1 on the right side. But then what? Well, I mean, ultimately what we're trying to do here is we're trying to undo Pemdas, which means we follow SADMAP. At the beginning, we would have tried to undo addition and subtraction, but that minus 3 is stuck inside the parentheses, which kind of act like a force field. We can't undo that until we undo the numbers on the outside. So we couldn't get to the addition subtraction. We could get to that multiplication, though. So we undid the multiplication. There's no division here, but now there is an exponent. Unfortunately, at this point in time, we don't know how to undo an exponent, like a square or a cube. Remember last unit we had an x power. We didn't know how to undo that either. We had to use some trickery. And so from here we kind of get stuck. Now again, later on in this unit, we are going to learn how to undo an exponent of 2. But for now, we're kind of up against a wall. Luckily, though, if we think back to last semester, we learned a different way to solve equations. We learned it in our System of Equations unit. You can go back to our Topic 4 unit, and I think it's in Topic 4, maybe lesson 3, give or take. And we learned that a single equation, and we'll zoom in on the bottom of this page here, a single equation like so, whoops, that was supposed to be a highlighter, there we go, actually has 2 parts, the left of the equal sign and the right of the equal sign. And using properties of systems of equations, we can actually split up this single equation into 2 separate ones. We can do f of x, or y, equals the left side of the equal sign. And then we can also do g of x equals the right side of the equal sign. So just showing you where those came from. Here's one, and here's the other. You can do this with any equation. And in fact, it's a very, very powerful tool to solve an equation, because there are many equations that we'll learn that we just don't know the algebra. In fact, the algebra might not even exist to isolate x. But graphing is actually a pretty straightforward process. And if we can graph a system of equations to find a solution, it's just as good as solving. It might take a little longer, but for today, that's what we're going to practice. We're going to go through and graph each side of this equal sign, and we'll start with f of x. F of x equals 2 times x minus 3 squared. Well, as soon as we see that square, we know it makes the shape of a U. It's a parabola. And we should probably identify the vertex. Opposite of h, comma, what is k here? Oh, let's put a plus 0 just so we can see the k. So we learned last class 3 comma 0. We can use the a value to go up 2 to the right one and up 2 to the left one. We also learned last class that we could go through and we could figure out the y-intercept. Except we don't actually need the y-intercept here. There will be some problems down the road where you will need the y-intercept, and actually I'm going to identify those right now. You'll definitely need the y-intercept on 4 and 5 on your practice problems on the next page. So I'm going to go ahead and just remind you that you'll need the y-intercept here. Okay. So let's go ahead and finish this off. So here is my parabola, something like this, something like that. Then we also have this equation in green, g of x equals 2. Well, that's pretty darn similar to our opener, h of x equals negative 4. So I'm pretty sure this is going to make a horizontal line which passes through the y-axis. In fact, it passes through the y-axis at 2. Here is my horizontal line. Well, we've gone ahead then and we've taken this one equation and turned it into two graphs. How does that help us? Well, we should be able to look at these two graphs and determine, oh look, the point of intersection on the left is 2, 2, and on the right is 4, 2. So if you were asked to solve this equation, what would our solutions be? Well, they would be the x values, the 2 and the 4. X equals 2, x equals 4. And that's it. So jumping back up here, our answers then to this equation where we got stuck are x equals 2 and x equals 4. And I'll close those curly braces. Oftentimes we write solutions with these curly braces just so we know there's a bunch of answers, and we don't use parentheses or anything because then you might think it's a point or an interval. All right, well, for today, you actually have a chance to move around and work with other people in class. Or if you're working at home, you'll work on your own. There are 12 questions over the next 2 pages. Your goal is to go through and do the same thing that we did in the example here. You need to take the single equation and split it into 2 separate equations. And I'll give you the starting point for the first 2. So here's a left side of the equal sign, a right side of the equal sign, and here are our 2 equations. We have x minus 2 squared plus 1, that's a parabola, and y equals 2. Over here we have negative 2, and I'm actually going to space this out because a lot of my students had trouble with this, and then 2x plus 1. Zooming in quickly, you'll notice that I split apart the x and the square. That tells us that there is an invisible 0 as the h here. That way we can see our vertex. Also, this 2x plus 1, that's a line. That's mx plus b. Okay? So you have 12 questions. Your goal is to work with a different student for each one of them. But either way, you need to find where the 2 graphs cross and then find their, it says approximate. I think I tried to pick these so you can find the exact solutions for each one. Once you're done with these 12, you can unpause this and see how you did. Ready, set, go. All right, you're back and you're probably hungry for those answers. My guess is there are probably one or two of these that tripped you up too, or you're not quite sure if I meant to do that, and I guess we're going to find out right now. So let's go through quickly. If there are any questions or anything I go over too fast, please just leave a comment and I'll do my best to respond back to you. So, problem one. We certainly have a parabola. The giveaway is that square. And our vertex, of course, will be positive 2, positive 1. Looks like that. We can get a little bit more accurate by putting that invisible 1 out front, up 1 over 1 in each direction. I did mention you probably won't need the y-intercept here, so I'm just going to go ahead and sketch in the graph, and who knows where that y-intercept is. Our second one in purple, y equals 2, horizontal line. Yeah, we didn't need that y-intercept, did we? Because I see my two solutions here, and I'm just going to circle the x for each solution just to make it clear that my approximate exact solutions are 1 and 3. Let's look at our next one. So it can be pretty tricky. I like to think of the graph as of x squared as just being at 0, 0. And then we added 1 to it, which moved us up 1. So if we went from 0, 0 to 0, 1, that's our vertex right here. However, our a value is negative 2 over 1, so down 2 over 1 in each direction. And so we have that slightly skinnier or vertically stretched parabola. Looks something like this. And then we have our mx plus b, right? We have our slope and our y-intercept. So we start at 1 and go up 1, 2 over 1, like so, or going the other way, down 2 to the left 1. And in fact, by following that, I think we can already see where our two intersection points will be. So even if you're not super accurate, we can definitely see this line will only cross twice. I think you'd have a very tough time getting a line to cross a parabola more than twice, but if you can figure out how to do that, be my guest and show me. It seems like we have intercepts of negative 1 and 0 that are here. There we go. Third one. Oh, I see two parabolas on this one. Right? We were using blue and purple. So I'll just continue through. We have blue and purple. The one in blue, x minus 2 squared plus 2. Let's start with that. To the right 2 and up 2. Not bad. Up 1 over 1. Up 1 over 1. Then we get this cool little parabola guy going up here. And then in purple, x minus 2 squared plus 3. This one is going to be right 2 up 3, kind of just above the vertex, kind of nestled in that little parabola valley there. Same a value, up 1 over 1, up 1 over 1. So then my students were definitely thrown off by this one. They're like, well, wait, what's going to happen? Is that purple parabola just going to cross out here like so? Well, I don't think so, because my purple parabola has the same a value as the blue parabola, which means their steepnesses are going to change at the same rate. But the purple parabola is one higher than the blue one. So that means that the rate of changes are actually going to parallel each other as they go up, and they're never actually going to cross. And so if they never intersect, do you remember what that means? That's right. There's no solution. If you were able to solve this by hand, you would get a false statement at the end. All right, let's look at 4. 4 is the first one I mentioned you'd probably need a y-intercept to help you out with. That ties back into 7.2. So x plus 2 squared minus 3, and then y equals 1. Before I find the y-intercept, though, let's not trust me here because, I mean, you should always question, right? So left 2, down 3. And then up 1 over 1. I'll just go 1 in each direction to make our life easy. And then what's the second equation? Y equals 1. That's our horizontal line. Now we can see the issue, right? If the y-intercept for the blue parabola is like down here, then we'll intersect somewhere over there. If the y-intercept is up here, then we're going to intersect something like that. So we need to actually find that y-intercept. A reminder, though, that's not too bad. We just take the x and replace it with 0. I would just follow Pemdas from here. This is 2 squared, which is 4. 4 minus 3 is 1. So that creates the point in x of 0, a y of 1. Looks good. Notice you can see that axis of symmetry right here. And so my y-intercept is 2 spots away from the axis of symmetry, so we go 2 on the other side as well. And now we have not only a fairly accurate parabola, but also 2 clear solutions. One at -4, one at 0. There we go. So we're flying through this. Fifth one, another parabola, nothing bad. I'll put that invisible 1 that's out front. It's great to get all this practice here. And then -3 for the second. Okay, left 2, up 1, down 1 over 1. And I said the y-intercept will be helpful, so I'm actually going to trust my advice this time. There we go. And so we get -1. This is 2 squared again. That's 4. We get -4 plus 1. Looks like -3 is our y-intercept. And let's see, that's 1, 2 away from the axis of symmetry, 1, 2 away right here. So we end up with our parabola opening down like so. And then y equals -3. Awesome. We actually end up with the same solutions as the last one, don't we? -4 and 0, even though the situation is different. The graphs are different. All right, let's move on. Let's see if 6 threw any of you off. So we'll start with that blue one. We have x plus 2 squared plus 1. So we know we start at -2, 1. A value will help us get 2 more points. And we end up with something like this. Then we go to our second one, negative. I'll put the 1 in front as well. X plus 1 plus 2. So HK forms, we start at -1, 2. That's right here. Do you see anything weird about this one? What's missing here? Yeah, there's no square. So if there's no square, this doesn't make a parabola. Well, if it doesn't make a parabola, then what do we do? Well, if it's just x to the first power, this makes a line. We actually first learned HK form with lines, so let's just create a line with a negative slope. Down 1 to the right one, up 1 to the left one. I think I might need to make this parabola a little bit more accurate too. And I didn't tell you that. I was hoping you guys would figure it out, or I forgot, but we'll never know. So let's see what happens. 2 squared is 4. 4 plus 1 looks like this is going to be 5. So here's this guy up here. And then symmetry, 1, 2, 1, 2. It should go up like so. There we go. And actually by doing that, we can see that our line passes through this parabola in 2 places. There we go. And it looks like my solutions here are going to be -4 and -1. You'll notice that I usually put the smallest solution first. It's okay if you switch the order, no one's going to yell at you. It's just a common technique. We usually put the most negative first for the solutions. Alright, let's continue out. 7 gives us 2 different parabolas. I know they're parabolas because of the squares. They're both in HK form, but they're each missing the K. There's that 0. We talked about it on the first page as well. Good practice here. So we have 3, 0, up 1 over 1. End up with something like this. And then we also have 1, 0, up 1 over 1. And we end up with something like this. Now, you might be tempted to ask if this right piece is going to intersect this guy over here. I don't think they will. If you look at this part and this part, I think they're the exact same graph, just shifted left 2 units. So I think this is an example of a parabola with only 1 solution, which is nicely just 2. All right, 8. Oh, we get a new symbol in here we haven't seen in a day or two. X squared. Let's give us that gap with the +1 at the end. That way we can see that there's that invisible 0 between the x and the square here. Tells us we start at 0, 1. Up 1 over 1 in each direction. Then I'm going to hold off. Who knows, maybe we need more points, maybe we don't, but that way I don't have to erase again. Let's go ahead and tackle this second guy that came out of nowhere. That looks like absolute value to me. We know absolute value can also be written in HK form. Looks like there's a 0 and a 0 missing. So I feel like we start at the point 0, 0. There's a negative 1 hiding out front. Tells us to go down 1 over 1 in each direction. This guy, don't forget, makes a V. It's pretty easy to use the slope here to get that V. There we go. And then our parabola, because this opens up, actually makes this pretty easy. This one is going to end up being no solution. All right, a couple to go. Let's go ahead and graph this. Oof, what are they doing? Looks like they're throwing these exponentials at us. Who came up with this? I did, but don't tell anybody. And then we have this one over here. So it looks like we have an exponential function, and we're looking for its intersection with a, what kind of function is this? Oh, there's no square here. This one makes a line. Well, the exponential function 2 to the x, I think we did on the first page. We know this is growth, the y-intercept is 1, and it grows up from here. Now, the question is, how mean was I to you? Meaning, do we have to be more accurate with 2 to the x? So let's get our line, negative 4, 3, 4 up 1, 2, 3, and then use our slope, down 1 over 2, down 1 over 2. Oof, looks like the math gods are smiling on you. This one only is going to intersect one time, and it's going to be, coincidentally, I think not, at the x value of 0, the only value we found on our exponential. All right, let's go a little further here. We're stepping into those exponential equations. Let's see what we can do. Negative 1 times 3 to the x. I'm actually going to do a little work down here, I think. I'll start by finding the y-intercept. That's replacing x with 0. Anything to the 0 with is 1. Negative 1 times 1 is negative 1. So my y-intercept for the exponential is negative 1. And then we also need to remember that this b value here tells us we are growing. Functions that grow always grow away from the x-axis as you move from left to right. So as I'm moving from left to right, we are going to grow away from the x-axis. Then we of course also have the equation x squared, which if you would like to put in the invisible zeros here, it's probably not a bad idea. We start at 0, 0, invisible 1 over 1. I think this one's not too bad. We should have this U-shaped graph again. I don't like that one curled back on itself. It should continue getting wider and wider. And I think we can pretty clearly see that these also don't intersect, which is good because I think if an exponential intersects with a quadratic, you can have a lot of pretty gross numbers there. All right, a couple more. We're deep into exponential territory now, but you guys are old pros at this, so you probably don't even need me to explain it. We're going to find the y-intercept. Hopefully you can see that for both of these, the y-intercept is going to be 1. So that's already a nice intersection point, right? So we have 1 for the blue function, but also 1 for the purple, and I'll kind of have them share that point. But then this blue function is growth. So our blue function starts along the x-axis and grows up, up, and away, versus our purple function is decay. If you multiply by a half, numbers get smaller. So my function is going to start pretty high up here, and it's going to decay down and then sit along the x-axis. Where do those two intersect? Well, it pretty much looks to me to be 0, aka the y-intercept. Alright, last one. Okay, we have an exponential function again, 3 to the x. We know the y-intercept will be 1, and this is growth. Grows pretty steeply because of that 3 times 3 times 3 times 3. Our second one has those absolute value bars, which means we make a V-shaped graph. We start at 2, 1, 2, 3, 4, 5. Uh-oh. And then we go down 2 over 1. Down 2 over 1. Down 2 over 1. this one could be pretty darn tricky. I might want to make this a little bit more accurate. Oh, but wait, doesn't it also go down to the left one? There we go. Something like this. That's looking pretty good. I'm going to improve the accuracy of my blue function though, and the way I'm going to do that is I just want to be more accurate on this side, so I'm going to substitute in 2 and 1 and 0 just to see what I get. So I'm just actually going to make a quick little table here. Input, output, I'm doing 3 to the x power, and I want to do 0, 1, and 2. Well, 3 to the 0th is 1, 3 to the first is 3, and 3 squared is 9. So I have a couple points here, right? 0, 1, 1, 3, and 2, 9. Let's get those on my graph. 0, 1, I know, they share the y-intercept. 1, 3, and then 2, 9 is way up here. So I think my graph looks something like this, goes through, and then goes way up here. That's actually enough to crack this case wide open, isn't it? Because we have this V-shaped graph, and my V-shaped graph intersects in 2 spots, at an x of 1 and an x of 0, right? We see those two? And the V-shaped graph is never going to intersect again. So we end up with 0 and 1. Nice. All right, now that we've finished our graphing practice, our solving by graphing, let's get on to our last page. You can choose one partner total for this last page, anyone you'd like to work with, and this one won't be too bad. We're basically going backwards. I'm going to give you what I want the graphs to look like. Then you need to make those graphs, and, this is tricky, write the equation that the two graphs are visually solving. So, I'm going to give you mine, but of course the challenge is going to be you need to do yours, and they should be probably different than mine. I think the odds of you picking the exact 6 graphs that I do are pretty darn slim. So, you guys of course should give this a shot, and then come back through, and we'll see how you did. Ready, set, go. Alright, sketch the graph of one parabola and one line that has 2 solutions. Well, let's see, 2 solutions mean they intersect in 2 spots. So I'm going to go ahead and pick 1, 1. Then I'm just going to have it go up 1 over 1, up 1 over 1. That looks pretty good. Here's my parabola, like so. And then, let's see, let's maybe write the equation of that parabola first. So we know it's x minus 1 squared plus 1. Right? That gives me the vertex 1, 1. Then I need a line that will pass through this that has 2 solutions. I bet I could make a line that goes through these 2 points pretty easily, because that slope is just a simple -1. And then I think that'll give me 2 solutions, won't it? Right? So how do I write the equation of that line? Well, the slope is down 1 over 1, so -1 for the slope, x, so it's going to make a line, and then my y-intercept is 2. This graph demonstrates y equals -1x plus 2 and y equals x minus 1 squared plus 1. They intersect in 2 spots. We're good to go. All right, part B. Sketch the graph of 2 parabolas which has 1 solution. How do we make 2 U-shaped graphs with 1 solution? We actually saw one on the previous page, but I'll give you a different one. All right, I'm going to give you one graph that opens up from here. And I'm going to give you a second graph that also starts at 0, 0, but opens down. Wouldn't that do it? Looks to me like they have 1 solution. Can we see how to write those? Well, I bet I could just do x squared, because we learned earlier that x squared is the same as x minus 0 squared plus 0, equals, and then this is actually the same graph as x squared, but it's just reflected. So equals -x squared. All right, part C. Sketch the graph of one parabola and one line which has no solution. There are many ways to do this one. Let's go ahead and do a downward facing parabola. So we'll do something like this. Just keep the a value of 1 to make our lives easy. So this parabola, zooming in, The vertex is negative 1 comma 1, so I need x plus 1 squared plus 1. And let's see, we need a line that has no solution. Well, I think we could just bump it up a little bit. And I don't know, we'll just pick this point again. And what if we went down 1 over 1? In fact, this is, I think, the same line that we did earlier. And so that would mean we have a y-intercept of 2 and a slope of negative 1. There we go. No solution. Part D, sketch the graph of a line and an exponential that has one solution. All right, well, I'm going to make my exponential be a little bit trickier here. Okay, so it's a little bit tough to maybe for you guys, especially to write an exponential, because you usually need a couple points. So I'm going to go ahead and have mine start at negative 2. And then I'm going to go ahead and double negative 2 to get to negative 4. If we double moving forwards, to go backwards we take half of it. And so half of negative 2 will be negative 1. Half of negative 1 is a half, and so on and so forth. So here's my exponential graph, but what's the equation? Well, the y-intercept is my a value. We've discussed that before, and I'm doubling every time. And I think if you graph this function, you'll see that it matches. Then we need a line, and it has to have one solution. But lines are so easy to write, especially in HK form. Let's say, for example, I want the solution to be this point right here, negative 1 comma negative 1. Well, HK form, x plus 1 minus 1. There's a line that starts right there. You could put a slope if you want, 1 or 2 or anything like that. I'll put a 2 in front for good measure. So go up 2 over 1, up 2 over 1, down 2 over 1. And look, now we have a line which passes through our exponential and has one solution. 2 to go. Sketch the graph of two parabolas which have two solutions. Oh. This one could be a little bit trickier, but I have an idea or two. Let's go ahead and start with one parabola that starts at this 2 and goes up 1 over 1 like so. This is going to give me a parabola like so, and an equation of x minus 2 squared plus 0, which I'll leave off, 2 comma 0. Then I'm going to go ahead and do a downward facing parabola whose vertex is at 2, 2. So x minus 2 squared plus 2, and I'm going to make it downward face with a slope of negative 1, or just a negative. Down 1 over 1, down 1 over 1. And this gives me a very nice parabola with, of course, two solutions. Last but not least, sketch the graph of one linear absolute value equation in one parabola which has one solution. Ooh, tricky, tricky. I'd argue that there's probably only one style of graph here that's going to have one solution. I think pretty much any other way you do it, yeah, I'm just trying to think here. I think pretty much any other way you do it, they're going to intersect each other in two spots. So I think the only way to do this is to start with a parabola. Doesn't matter where. I'll start down here, I guess. And sure, I'll make it downward face. Why not? Down 1 over 1, down 1 over 1. So here's my parabola. Equation-wise, x plus 2 squared minus 2. That's negative 2, negative 2. Downward facing parabola needs a negative. Then I'm going to write an absolute value graph that has the exact same vertex. X plus 2 minus 2 puts me right here. But I can't have the parabola go down, the absolute value go down, because I think then it could actually end up intersecting 3 times. We got 3 solutions there. That's pretty wild. I'm going to have this just go up with a boring up 1 over 1. You could pick any, I think, positive slope here, though. And now we have an absolute value equation that only has one solution with our parabola. Okay, well, hopefully today really helped you solidify how to graph our 4 types of functions: lines, linear absolute value, exponentials and quadratics. If you do have any questions, and I know those exponentials can be pretty tricky, don't let those stress you out too much. You're going to do a lot more of them in Algebra 2, so we kind of just do a quick maybe survey of them in Algebra 1. But if you do have any questions, as always, leave a comment. I'll get back to you. And thank you for working so hard on topic 7.3, solving quadratics by graphing.